Okay, so today we're going to talk about section 5.1. Here we're going to develop the groundwork to connect what we were doing in section 4.9, antiderivatives and indefinite integrals, with the area under a curve. And you guys have been dealing with area since as long as you've been doing math, just about, right? You had area of a rectangle is length times width, and area of a triangle 1/2 base times height, and then area of a circle pi r squared, right? And these first two were pretty easy to see. You could explain to an elementary school student where these formulas come from, but this one, my guess is they never really explained to you. And the reason they never explained is because you need calculus in order to prove this area formula. And so that's what we're going to kind of be moving towards with this section, is being able to take areas under curvy things. A better way to put that, under curves, right? So for example, if we look at number 1, they want us to use rectangles to estimate the area under the parabola y equals x squared between 0 and 1. And once we get good at estimating the area under a curve, then we can start looking at how to actually find the area under the curve. So let's go ahead and sketch this real quick. So basically what we're going to do is we're going to find the area of several rectangles and use that as an approximation for the area under the curve. And at this point, they don't specify how many rectangles we should use. Let's go ahead and use 4 to begin with. And to start, we're going to go ahead and break up our x-axis between 0 and 1 into 4 evenly spaced subintervals. So we're going to put a 1/2 here, a 1/4, and 3/4, like that. And then from each one of these, I'm going to draw a rectangle. So maybe in green right here, I've got a rectangle that is going to go up to the curve like that. That's a little sliver of a rectangle there, if you will. And then maybe in purple, I'll go here and get another rectangle like that. And let's go on to orange, draw another rectangle. Notice the height of each rectangle is going up to the function. And then we'll do one last one here in this color, all the way up to there, like that. Now, how hard is it to find the areas of these rectangles? Not super hard. First of all, notice they all have the same widths. Pretend they look evenly spaced. I know I didn't do a great job of that, but each one has the same width. So let's go ahead and call that width, right? I'm talking about the distance from here to here. Let's call that delta x, or change in x. And delta x, the way we're going to find it is we're going to take the distance from 0 to 1, which is 1 minus 0, and we're going to divide it by the number of rectangles, which in this case is 4. And so this easily becomes 1/4. That is the width of each one of these rectangles. Now, from there, what we're going to do is we're going to find the area, for example, of, let's look at this one in back first. Okay, I think it's just easiest to look at. It's a little harder to look at that green one in front. If we wanted the area of that rectangle, we would multiply base times height, or length times width, using this guy right here, right? So if I want that area, we can say that the height of our rectangle is going to get multiplied times the base. Well, we know that the base is delta x, or 1/4. So I'm going to take 1/4 times the height. Well, what's the height going to be? The height is going to be from here in yellow all the way up to there, right? The highlighted yellow distance. Well, all that is the value of the function at 1, right? The value of the function at 1, and when x is equal to 1, you put it in there, you get x squared. 1 squared is 1. This value is 1. So we're going to multiply by f of 1. And so that's the area of our pinkish rectangle there. Okay, now we're going to do the same thing in orange, let's say. Let's go and do that one next. Doesn't matter the order in which we do these, right? Adding up areas, you can do it in any order you want. So we're going to add onto this the base in orange, 1/4, times the height in orange. Well, that's going to be, again, highlighting in yellow, that's going to be that height there, which is simply the value of the function at 3/4. So I'm going to multiply this by f of 3/4. And then we'll continue on to the purple right here. The purple rectangle. That also is going to be the base 1/4 times the height where our rectangle goes up to the curve at x equals 1/2. So that height is going to be f of 1/2. And then finally, that little green rectangle in there, right? We're going to find this area here. And that's going to be, again, 1/4 times the height of the rectangle would be the value of the function at 1/4. And we're going to add all those up. And that is going to be the area of our 4 rectangles added together. Okay, so this is area, or I'll say total area of 4 rectangles. And the math on this isn't really particularly hard, right? Notice, first of all, we can factor out a 1/4, and we're going to get f of 1 plus f of 3/4 plus f of 1/2 plus f of 1/4. And plugging these values into f, it's just, well, remember what the function is. The function is squaring, right? So I just have to square each of these values. 1 squared plus 3/4 squared plus 1/2 squared plus 1/4 squared. And we're going to get 1 plus 9/16 plus 1/4 plus 1/16. That's going to give us what? 10/16. Here, let's just make it all over 16, right? So this guy's 4/16. This one's obviously 16/16. So I'm adding up 10, 14. Do I get 30/16 like that? We can cancel. So we're going to get, here we'll get a 2, here we'll get a 15. We'll get 15/32. And so what we've done is we've estimated the area under the curve with the sum of these 4 rectangles. And you should be saying to yourself, that's a really cruddy estimate, right? Because look at the curve. The blue curve, if I can zoom back in here, the blue curve is cutting through each one of these rectangles. And all of this rectangle area that you have up here in yellow, and that, all that bleed over, if you will, is too much area, right? So the actual area under the curve is going to be less than this, okay? But to start off, we start off with an estimation. And this is maybe not the best estimation, but it's going to be a start, okay? Another thing I want to add real quick before we kind of move on from this is in this whole section and in the next, the letter N is going to equal the number of rectangles, okay? So N is the number of rectangles. And what I'd like to do is I'd like to show you where we're headed with this before we start getting into more examples. So I'd like to look at GeoGebra and show you what we can do with this approximation with a little bit of calculus, as we'll see soon. So here's the problem we just did. You'll notice that we have our function f of x equals x squared right there. And we are looking at the area under the curve, or we're approximating the area under the curve from 0 out to 1. And we have our 4 rectangles just like we saw. And you'll notice right here, we have the area of these, the sum of the area of these four rectangles is 0.4687, which if you put 15 over 32 into your calculator, that's what you're going to get. So all that's good. Now, what I'm about to show you is really the basis for finding the area under the curve. Okay, we did this with four rectangles. Why four? That's what I chose. We could have done this for more rectangles or for fewer rectangles, right? We could have done one rectangle like this, and that would have been an even worse approximation than we got, right? But as we increase the number of rectangles, remember n represents the number of rectangles. As I drag this, there's 2 rectangles and 3 and 4, 5, 6, 7. Here I'm up at 10 rectangles, almost. Somewhere in there is 10 rectangles, right about there. That's a much better approximation than the 4 we saw a moment ago, right? Remember, 4 looked like this. And so all those extra bits of area of the rectangles that are over the curve, those are unnecessary, right? We would like those to get smaller and smaller. So the way we do that is we do the same problem, but for 10 rectangles. And if you think, okay, that's good, but there's still lots of area that goes above the curve, you're right. So maybe we should go to 20 rectangles. That's even better. Okay, maybe we should go even further. Let's go to 50 rectangles. And all of a sudden you're noticing the more rectangles you have, the better an approximation you get of the area under the actual area under the curve. So look what we have now. We have 0.3434. Okay, but why stop at 50? Why not go to 75? There's 75 rectangles, 76, 0.3399. And we have much less area over the curve, right? These little steps, if you will, are those little bits above the curve are the extra area that we don't want. So we let our number of rectangles get even bigger. And here we have 100 rectangles. And again, if you look at the little areas that are above the curve, they're much smaller. The sum of those areas is much smaller than what we got with only 4 rectangles, right? So the idea is the same as what we just did. It's just we want to do it for a lot more rectangles. Maybe we do it for 100 rectangles. That sounds like a lot of work, right? You got to find all these areas and add them up. What about 1,000 rectangles or 10,000 rectangles? Because the more we do, the closer the sum of the areas of those rectangles is equal, or the closer it gets, I should say, to the area under the curve, okay? Our goal is to get to this area. Whoops, that's not what I wanted to hit. That's not what I wanted to hit. There we go. Our goal is to get to that area there. And the true area is this number here, which we're going to learn how to get there, all in good time. But you'll notice that as we increase the number of rectangles, look where it says upper sum, we get numbers that are approaching 0.3333, right? They're getting closer and closer to that. And that sounds a lot like something we've done earlier in the semester, which is a limit. So that's where we're headed. We're going to take the sum of a bunch of areas of rectangles, and then we're going to let the number of rectangles go to infinity. And that's going to be our limit as the number of rectangles goes to infinity. Now, we'll come back to this figure as we go on to the next problems. And it sounds very daunting at first. Oh, we're going to add up 1,000 rectangles? That's ridiculous. Well, that's where we're headed right now. We're going to come up with ways of doing that in a reasonable manner. Now, the rest of this section is going to be allowing us, it's going to give us a way to add up lots and lots of rectangles in a very efficient way. In order to get to where we're headed, we need to get comfortable with sigma notation, also called summation notation. Okay, so this right here, this big Greek letter is a capital sigma, and it means add up a bunch of stuff that comes after it. We have our upper and lower bounds of summation. Here we have I equals 1. That's our lower bound of summation. Here we have n, which is our upper bound of summation. And basically what it means is we're going to plug in 1, then 2, then 3, then 4, and so on and so forth into I in this expression, and then add it up over and over and over again until we get to plugging in n like that. So if we look at example 2, evaluate each of the following. So here we're going to be adding up I, where I starts at 1 and goes all the way to 8. So we're going to have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. And adding those up, we should get 36, I think. Okay, so that's how we use sigma notation. With the next one, we are taking j's starting at 2 and going all the way to 6, and we're squaring each one of those numbers. So we start with 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, right? We're stopping here at 6. And so we have 4 plus 9 plus 16 plus 25 plus 36, and I get that equal to 90. Now, with the next one, we have k's starting at 3 and going to 6, and we have this expression, right? 1 over n times 3 squared minus 2 times 3. I'm starting with 3 because that's what k starts at with our lower bound of summation. And then we're going to add to that the same expression with a 4 plugged in for k. Add it again to 1 over n times 5 squared minus 2 times 5. And then one more time with 6 squared minus 2 times 6. Now, one thing to notice is we have 1, 2, 3, 4 terms, and they all have a 1 over n. So we could factor that out. We could put 1 over n here, and then we're going to get 9 minus 6 plus 16 minus 8 plus 25 minus 10 plus 36 minus 12. And we can do this math pretty quickly. I'll just tell you what I got. I got 50 over n. But I want you to notice that we factored out that 1 over n, right? And so one thing we can do with summation notation is we could have factored out the 1 over n way over here and put it on the outside. Because it doesn't have any k's involved with it, we're allowed to do that. And I'll show you that in future examples. This next one, we have f of m sub I times a delta x, and I is going from 1 to n. Okay, so what's that going to look like? I'm going to rewrite it here. I equals 1 to n f of little m sub I delta x. So we're going to evaluate f at m sub 1, and then we're going to multiply that by delta x, plus little f evaluated at m sub 2 times delta x, plus the same thing at m sub 3 delta x, and this is going to continue all the way until we get to f of m sub n times delta x. And you might think, boy, that one's not very exciting. There's no calculations to do. True, but this one is actually closest to where we're headed with finding areas of rectangles. So what I want you to notice here is we have a delta x here. That is a width of the rectangles, right? As we saw in the previous example, in example 1. And over here, this f of m sub I is going to be the height of our rectangles. And as you know, height times width is going to give us the area of the rectangles. So we are adding up a bunch of areas of rectangles, which is kind of cool. And that's, again, where we're headed. Okay, now let's go ahead and look at some properties of summation and some summation formulas that will allow us to add up a whole bunch of rectangles or areas of rectangles in an easier fashion, and then apply them to an example. So here we have two properties. The first property, which you're seeing right here, that's where we can factor out a constant that's inside the summation, factor it outside, just like we saw in the previous example with that 1 over n, I believe it was. And then with this next one, we can always write the summation of a sum or a difference by splitting the summations up into two summations that are either being added or subtracted. And we'll do that in the next example. Next, we have these summation formulas where we're able to add up a bunch of numbers without actually adding one by one. Okay, and so we've got the first one where we can, right here, where we can multiply a constant n times. So we multiply the constant times n, nice and straightforward. Here we can add up the numbers 1, 2, 3, 4, 5, 6, 7, all the way up to n using this formula. And as a matter of fact, I think a moment ago with the previous example, in example 2, part A, we did this from 1 to 8 and got 36, right? In other words, we can take the sum I equals 1 to 8, and using this formula where n equals 8, we get what? We get 8 times 8 plus 1 over 2. And that's simply going to be 4 times 9, which is 36. That was way faster than adding up all those numbers, right? So that's kind of nice. We have two other formulas here. This one right here, where we are adding I squareds. We'll use it in a moment. And then we also have this one for adding I to the third. I'm not going to prove these here. These proofs require a method called proof by induction, which is worthwhile to see, but it's not the best use of our time right now. But by all means, come by office hours if you want to see why these things are true. I'll be happy to go through it with you. So let's look at example 3 here. Find the sum of the terms I minus 2 quantity squared for I equals 1 to 2 to 3 to 4 all the way up through 50. Rewriting this with summation notation looks like this. We want the sum I going from 1 to 50 of I minus 2 quantity squared. Now, our goal is going to be to rewrite this expression so we can use the summation formulas above. So we'll go ahead and square the expression I minus 2 and get something like this. And now we'll go ahead and use this property of summations to split up these three terms into three separate summations. Next, we'll use this property here to factor out this 4 in this middle summation, so it'll look something like this. From here, we're going to use the summation formulas above. So right here, we're summing 50 I squareds. We can use this formula right here. Here, we're summing 50 i's, and we'll use this formula right here. And finally, right here, we're summing 50 4's, right? 50 constants, which are all 4, and we'll use this formula right here. So our blue summation, we've got n equals 50. The 50 is right here, so we're going to plug in 50 into each one of these n's and get something like this. So that's what the blue summation becomes. Minus 4 times. Now we're going to take our 50 and plug it in here and here. And that's what our green summation becomes. And finally, we've got a 4 for our constant in the yellow summation, and we're going to multiply it by 50 here. So that last yellow summation becomes 4 times 50. The rest of this is just arithmetic. Pause the video, work this out for yourself. I ended up with 38,025. Let's go to example 4. So the first thing we're going to notice is that we have three terms that are being added up. And so we're going to go ahead and use this property here to split it up into three summations. But then we're also going to use this property here to rewrite it, factoring out all the constants. Okay, so that means we're going to get something like this. First, we're going to have the summation I equals 1 to 4 of negative 1/8 I squared. We're going to add to that the summation I equals 1 to 4 of 1/4 I. And we're going to add to that the summation I equals 1 to 4 of 23/8. And so we've just done this property right here. That's kind of nice. Now we notice that we can take out a constant, here a negative 1/8 and here a 1/4, and we'll go ahead and factor those out. So we get negative 1/8 times the sum I equals 1 to 4 of the I squareds, plus 1/4 comes out, the sum I equals 1 to 4 of just plain I, and then here we're going to have the sum I equals 1 to 4 of 23/8. So now that we have it split up like this, we can use our summation formulas. And so we're going to go ahead and start with this one right here, right? We're going to add up a bunch of I squareds, and we just so happen to have a formula for that right there. So we're going to start with this guy. And n is equal to 4, right? That's the upper bound of summation. So this is going to become negative 1/8, and then we're going to multiply that by 4 times 4 plus 1 times 2 times 4 plus 1 all over 6. So we replaced our summation of the I squareds, I equaling 1 going all the way to 4, with this in green. That is a summation formula. And then from there, we're going to switch over to this formula here in blue, right? We're going to use the sum of the i's is going to be this formula here, where n is equal to 4 again. So we're going to get 1/4 times, we're going to have 4 times 4 plus 1 all over 2. And then finally, well, let me make sure we have all our colors coordinated here, right? We just did that. And then finally, we're going to use this guy right here when we add up a certain number n of the constants, right? We just multiply. So here we're going to get plus 23/8 times 4, right? C times n, the constant times the upper bound of summation. And so we just use that formula to go from here to here. And so now this problem boils down to a whole bunch of arithmetic, right? So we have negative 1/8. On top here, we're going to have 4 times 5 times 9 all over 6, plus here these 4's will cancel, so we'll have 5 over 2, plus here the 4 and this guy will cancel, leaving us with the 23/2. And so now I think we can also cancel a little bit here. Let's go ahead and cancel that here, giving us a 3 and a 2. We can cancel here and here, leaving us with a 2. So I think we have negative, there's a 5 times a 2 times a 3 times a 1, to a negative 1. So I think that's negative 30/8, plus adding these guys back, I think we have 28/2. And we can simplify this guy to negative 15/4 plus 56/4, and that gives us 41/4, okay, which can be written as 10.25 if you prefer. And so there we've used both of our properties of summation, and we've used 3 out of the 4 formulas for summation, right? And by doing so, we were able to add up whatever this guy in here represents, and we'll talk about it later. We're actually going to come back to this problem later on. I picked this for a reason. Whatever that represents, we just found its sum without actually having to plug in 1 for the i's and then add it to what you get when you plug in 2 for the i's and 3 and 4 and then add all that up. So there's that one. Example 4, we're going to evaluate this summation here. We're summing I going from 1 to n of I minus 1 over n quantity squared times 1 over n for n equals 10, 100, and 1,000. Okay, so notice what we're doing here. Here, we're going to be adding 10 of these, right? I equals 1, I equals 2, I equals 3, all the way up to 10. And adding 10 things isn't that big of a deal. But here, we're going to add 100 of them. Yeah, that's a lot. That sounds like it might take quite a while. Well, just wait till we do this one. This one's 1,000 of them, right? 1,000 of these things that we're about to add up. But the good news is, because we have our summation formulas from above, we're going to be able to actually do this very efficiently. So let's go ahead and start and do this in general for n. And then once we have an expression that will give us the summation, then all we need to do is plug in 10, 100, and then 1,000. So here we go. We've got the sum I equals 1 to n of I minus 1 over n quantity squared 1 over n. And our goal is to rewrite this in such a way so we can use these summation formulas over here. So that's our goal. All right. So what we're going to do first is we're going to square this and multiply in the 1 over n and see what it looks like. So we're going to have the summation I equals 1 to n. When I square the numerator, I'm going to have I squared minus 2i plus 1 over n squared, and that's being multiplied by 1 over n. So we can just multiply the denominators here, and we get n cubed in the denominator, like that. And so just as we saw in the previous examples, we can factor out anything not involving i's. In other words, we have a 1 over n to the third here, which we can write on the outside of our summation like this. I squared minus 2i plus 1. Now we're going to use our properties with summation to split this up into 3 different summations like this. So we have our 1 over n to the third times, we're going to have the sum I equals 1 to n of I squared minus 2, I'm factoring out the 2, the sum I equals 1 to n of I, and then plus the sum I equals 1 to n of 1, like that. So we have our 1 over n to the third. And now we get to use our summation formulas. And so if we look over here, we notice that in green, we have the sum of the I squareds. And in blue, we have the sum of the i's. And in yellow, we have the sum of constant a bunch of times. How many times? N times. So we're going to fill those in right now. So starting with the green formula, we're going to have n times n plus 1 times 2n plus 1 over 6. And from there, we're going to have minus 2 times. Now we're going to take our blue formula, n times n plus 1 over 2. And then finally, we're going to have our yellow formula, which is just taking the upper bound of summation, which is n, and multiplying it times the constant there, which is 1. So we're going to have 1 times n, and there it is. So once again, this is our green formula. This is our blue. This is our yellow. And so now we get to clean all this up and then see what comes of it. So in green, in that numerator, we have n plus 1 times 2n plus 1. When we multiply this out, we get 2n squared plus n plus 2n plus 1. Of course, the middle terms combine. And this whole thing is being multiplied by an n, right? I'm looking at the numerator over here of green. And so if all this is multiplied by n, we're going to get 2n to the third plus 3n squared plus n in the numerator all over 6. Here we could cancel off these 2's, right? So we get just minus n squared plus n, and finally plus n in the back. Okay. At this point, we probably want to think about making common denominators. Let's actually go ahead. Let me come back here for a moment. Let's go ahead and distribute the negative for a moment and see what we get. So I think that's going to give us a negative n squared and a negative n there, like that. And of course, these n's in back will cancel off. So now we can write this as 1. Actually, let me write it over here. Move this out of the way because we're done with that. We've got 1 over n to the third times, we've got 2n to the third plus 3n squared plus n over 6 minus, making a common denominator, we're going to have 6 n squared over 6 like that. Combining our numerators there, we're going to have 1 over n to the third on the bottom. We're going to have 2n to the third minus 3n squared because we're combining this guy with this guy right there. And then we're going to have a plus n all over 6 like that. And of course, the n to the third can be multiplied in here. So I'm going to go ahead and do that. I'm just going to rewrite it so we have the n to the third on the inside like that. And then we don't need these brackets anymore. And that's where we are now. And it looks like we're in a pretty good place, but I think we can take it even further and turn it into a really nice expression. We can break it up into 3 separate fractions like this. And if you don't need to write this step, that's fine. Don't write this step, just go on to the next step. But I'm going to write it for now like this. And the first one is going to simplify, right? This one right here is going to simplify to 1/3. This one's going to simplify to 1 over 2n. And the last one is going to simplify to 1 over 6n squared. And so we've arrived at a very nice expression here where we're going to now be able to plug in different values for n quite easily. So we're going to start with n is equal to 10. If n is equal to 10, then the summation I equals 1 to 10, right? We're looking at this, the summation I equals 1 to 10 of I minus 1 over n quantity squared times 1 over n is going to equal this right here, plugging in 10 for each of our n. So 1/3 minus 1 over 20, right? 2 times 10, plus 1 over 6 times 10 squared, right? 6 times 10 squared right there is going to give us 600. And when you put this into a calculator, you add it up and do the work, you get 0.285. So there is what we would get if we added 10 of these guys in purple, right? I going from 1 to 10. All right, well, what happens when we go to 100? If n equals 100, then the summation I equals 1 to 100 of I minus 1 over n squared, 1 over n equals, well, again, we're going to use, here, let's highlight what we're going to use each time. We're going to use this each time, right? So we're going to use 1/3 minus 1 over 2 times 100, which is 200, and then plus 1 over 6 times 100 squared, which I think looks like this, 60,000. And adding all those up gives you something like this, 0.32835. And so in that case, you just added up 100 of these guys right here. Now that's pretty impressive. And we did it in a relatively short amount of time and with relatively little effort in comparison to adding up 100 of these. But what about if n equals 1,000? Oh my gosh, that's got to be insane. Well, here we go. Then the sum I equals 1 to 1,000. We're adding 1,000 of these types of terms here. Again, using what's in the pink box, 1/3 minus 1 over 2 times n, that's 1 over 2,000. And then down here, we're going to get 1 over 6 times 1,000 squared. So 1, 2, 3, 4, 5, 6, right? 1 times 1,000 squared is going to be, what, 6 million there? 1 over 6 million, which is going to give us 0.33283335. And so that last one, very impressively, we just added up 1,000 terms. That's pretty powerful stuff. And so then the question becomes, could we take the limit as the number of rectangles goes to infinity? Oh, I didn't mention these were areas of rectangles, equals 1 to n of this thing. So I kind of gave it away there. What we're going to see later, kind of like what we saw earlier. Let me back up for just a moment. Remember here where I had in green the heights of the rectangles and in orange the widths of the rectangles? Well, it turns out, as we'll see later, that what we have here is this represents the heights of a series of rectangles. And this is the width of those rectangles. Whoops. The width of rectangles. And so when we multiply height times width, what we end up with is the area, right? So really what we've done here is we've just added up the areas of 1,000 rectangles. That's pretty cool. And we could have done 100,000 or 1,000,000 of them with relative ease, right? It's just a matter of choosing n to be 1,000,000, right? So pretty cool stuff what we did there. We're going to come back to this particular problem in a future problem, but that's using the summation formulas, using the properties of summation, and getting us towards being able to add a very large number of areas of rectangles. So as we've already discussed, finding the area of rectangles is a relatively easy thing to compute for us. And as we've seen, we're going to use rectangles to approximate the areas under curved or with curved boundaries. And so we've already looked at this using GeoGebra. I'm just going to draw 3 quick drawings of what we're talking about and say a couple things about it. So I'm going to start off with 3 functions that hopefully look somewhat the same. And in each case, we're going to build rectangles going along the x-axis from, let's say, 0 to some value out there. So these three drawings really, they just depict what we saw earlier with the computer generated function, right? Computer generated graph, where we got more and more rectangles, right? So just to remember a few things here, let's say right there, we've got, first of all, let's call these functions f of x in each case. So each one of these is f of x. And again, I tried to make them look like they were similar. And so we count our rectangles, right? We're talking about areas of rectangles. So we're looking at the area here, plus the area here, and plus the area there, and so on and so forth, right? And so in this case, we've got 1, 2, 3, 4 rectangles. So we say n equals 4. I think here n equals 8, right? 1, 2, 3, 4, 5, 6, 7, 8 rectangles here. 1, 2, 3, 4, 5. Here I've got 12 rectangles, n equals 12. And in each case, it may not look like it in my picture, but I tried to make each of these distances the same, right? So here, this is what we call delta x. And here, this is what we call delta x. And as you can see, delta x is getting smaller the more rectangles we have. Now, delta x, which is the width of a rectangle, so rectangle width delta x, the way we're going to find delta x is we're going to take the distance from where we start to where we end. So let's just quickly write that in. If we call this A and this B, this A and this B, this A and this B, we're going to end up taking the distance between B and A, so B minus A, and then divide it by the number of rectangles n. And that's going to give us the width. And I'll mention that again as we proceed. From there, if we look, for example, at this first drawing, we have a point here at x sub 2 comma f of x sub 2, right? We might call this x sub 1, there's x sub 2, x sub 3, x sub 4. The subscript is basically saying this is the x value from the second rectangle that we're going to use to get the height of that rectangle. In other words, the area of the second rectangle is going to be f of x sub 2 times the width, which is delta x. That is area of second rectangle. Okay, but of course, as we do this for many, many rectangles, for example, in this last one, we will start talking about just an individual rectangle. So let's go ahead and just take this one randomly from somewhere inside here, and we call that the, here, let me put it, we call it the ith rectangle. So this right here is the ith rectangle. So I is counting out our rectangles. It starts at 1 and it goes all the way to n. And so this x value that we have right here is x sub I minus 1, and this x value is x sub I. And so we call this little interval that I'm darkening in here, we call that little sub-interval the ith subinterval. Okay, so inside there, we have the ith subinterval. And the area of the rectangle over the ith subinterval equals, well, it's going to equal this height here, right? Or if you want the length times the width. right? Well, that takes us to a point right here, which is x sub I is the x value, and f of x sub I is the y value. And so that red length is f of x sub I. So we're going to have the height f of x sub I like that times the width, which we've already talked about, is delta x. So that's the area of the rectangle over the ith subinterval. And so if we come up here, you'll notice that's what we have with each one of these, right? We've got, in each case, a height times a width. F of x sub 1 is going to be the height of the first rectangle times delta x, the width. And then you take the height of the second rectangle times the width. And you do that until you get to the nth rectangle. And so this is the sum of a bunch of areas of rectangles. How many? N of them. But then if we take the limit as the number go to infinity, right? As we get more and more rectangles, we're getting closer and closer to the area under the curve. And that's what the limit is doing there.